So what follows is a hand waving, or if you like, a heuristic derivation of the current equations which we've seen in the previous videos. Now first of all we're going to look at the equation of the IDS, that's the drain to source current in the linear region. So we start off by thinking about the area here below the oxide layer, and this is where the current flows, and this is where the inversion occurs. So we could say that across that layer, if we were to use Ohm's law, we could say that V equals IR, or equivalently we could say that the voltage is going to be directly proportional to the resistance. So as the resistance of this layer goes up, then we have a greater volt drop across the layer. If the resistance of the layer is low, then the volt drop across the layer was going to drop as well. So there's this direct proportion. But we're not interested in the resistance, we're interested in the conductance. That is how easily the charge is going to be conducted across the layer. Now the conductance is going to be given by 1 upon the resistance. And you can see that if you think about the voltage, as the volt drop across the layer increases, it must mean that the resistance must have gone up, so therefore the conductance, or that is the ease at which the current flows, must have gone down. So we can say here that our voltage is directly proportional to 1 upon R, and the 1 upon R is our conductance. Now we know that the conductance, or how easily the current gets conducted across this channel, depends on the depth of our inversion layer. Now what we could do is we could look at this in a simple manner. We could think about the conductance as being directly proportional to the depth of this inversion layer. But we could say it's going to be directly proportional to the average depth of it. So for example, we're going to have an inversion layer at this side here, which is going to be the VGS minus VT. So how much of the gate source voltage is above the threshold voltage. And that's going to give us a certain depth. Let's say this is the depth here. And at the other side, we're going to have the V gate drain minus the VT. And it's going to give us an inversion layer depth here as well, which is, let's say it's this depth here. So what we do is we say that the conductivity is going to be given by the average of these depths. So what we do is we take one of them, we add on the other, and we divide it by 2, and we'll get an average layer depth of something in here. So the average layer is going to be somewhere along this point here. So we're left with this equation that the conductivity is going to be the half of VGS minus VT plus VGD minus VT. So let's write this V gate drain out in terms of our V gate source and VDS, and we do that here. So we're going to have our half VGS minus VT, which is the same as this here, and we're going to have our VGS is the same as our VGD, is the same as our VGS minus VDS. So let's have a look at this little section here. So what we want to show is the V gate drain is the same as V gate source minus the V drain source. So if we first of all look at this little device here, we've got our gate, our source and our drain. We could say the V drain to gate, so VDG, that's this voltage here, is going to be the entire voltage VDS, V drain to the source, minus the V gate to the source. Okay, so this voltage here is going to be the same as this voltage here, which is the drain source, minus this little voltage here. But that's not actually what we're interested in. We're not interested in the drain to the gate. We're actually interested in the gate to the drain. So the gate to the drain is just the negative of these here. So it's just going to be our VGS minus the VDS. Okay, so we can rewrite this V gate drain as the same as V gate source minus VDS, and that's what we'll put in here. So this is just to get it into the correct format. So we'll have this thing here replacing this, and we've got the minus VT. So whenever we add these up, we're going to get VGS minus VT minus VDS upon 2. So you just add each of these terms up. That plus that divided by 2 gives us the VGS, and we're going to have the other terms here, VT minus VT minus VT is minus 2VT divided by 2, which just gives us the VT, and we've got our factor of 2 in here for the VDS. Now finally, this is going to give us the conductivity. Now the actual current is going to be given by our beta value times the voltage. So in effect, the current here, I is equal to V upon R. Okay, so it's going to be V times the 1 upon R. So we've worked out the 1 upon R here, and we're going to multiply it by our V. So our V here is the VDS. So we're going to have our beta, in this case if it's an NMOS device, we'll have our beta N times the VDS times all of this. So whenever we multiply this out, we're going to get our value beta N VGS minus VT all times VDS minus VDS squared upon 2, and this is our linear equation. So don't worry too much if you didn't understand all that, didn't follow all of it. I've just added it in as an extra because I don't want to just throw the equations at you. I want you to have some sort of idea of where they come from. So in this instance here, all you really need to know, the only thing that is really of value here, is to think about the conductivity as being the average of the conductivity over the depletion region here. So let's go ahead and we'll look at the saturation equation. Now we work out the saturation current using the same ideas that we did for the linear current. When the device is in saturation, we're going to have a pinch-off point somewhere along the channel, let's say a point X. The current that flows through the device is going to be given by the average, again, of the inversion layer depth. So again, we can say that the conductivity here is going to be given by the average of this depth of the inversion layer. So at this side here, the inversion layer depth is going to be given by our VGS minus VT. So this is how much the gate source voltage is above the threshold voltage at this side. Now the other side here, well, the inversion layer depth is simply a value of 0. And we divide these two by a factor of 2 to get the average. So it means that the conductivity is going to be given by this equation here. So finally, we can work out the current. So the current is going to be given by the VDS times this conductivity. So it's just I is equal to V upon R. So IDS is going to be this 1 upon R times the VDS, and we'll add in the process factor, which is the beta N for an NMOS device. So we simply take what we have up here and we multiply it by our beta N VDS. So that means we're going to be given the equation here is going to be given by the value beta N upon 2 times VGS minus VT all times VDS. But remember that in pinch off this VDS, it can be written as VGS minus VT. Now we've seen that in a previous video whenever we looked at the transfer characteristics. And we've seen that if we had the IDS here, and we have our VDS along here, then we've seen that we had a linear portion here, and then from the linear portion it then went into the saturation, and the point at which this occurred here was at the pinch-off point, and that pinch-off point is given by our VGS or VDS is equal to VGS minus the VT. So that's the corner point here. So we can put this value in, VDS equals VGS minus Vt for the VDS here, and we're going to be given the beta n upon 2 times VGS minus Vt all squared, and this is our saturation current. So again, you don't need to remember all of the details of this, you just have to remember that we can derive it again by looking at the average of the inversion layer depth here in order to give us the value for the current. So that's all for this video. I'll get you on the next video. Goodbye.